Welcome to today's problem walkthrough. In this session, we will explore the problem titled Check if all 1's are at least length k places away. This problem challenges us to validate a condition in binary arrays while considering constraints on spacing. Let's dive in to better understand the problem and solve it step by step. The problem requires us to determine if all the 1's in a given binary array are at least k places apart. To elaborate, you'll be given an array, nums, containing only 0's and 1's, as well as an integer, k. We need to ensure that for any two indices I and j where there are 1's in the array, the distance between them, calculated as j, I, must be strictly greater than k. If this condition holds true for all such pairs of 1's, we return true, otherwise, we return false. The input includes the binary array nums and the integer k, while the output is a Boolean value. For example, if nums contains no 1's or only a single 1, the condition is trivially satisfied, and the output will always be true. Let's look at an example to understand this better. Suppose the input array is nums equals 1, 0, 0, 0, 1, 0, 0, 1, and k equals 2. Here, the first one is located at index 0, the second one at index 4, and the third one at index 7. The distance between indices 0 and 4 is 4, 0 equals 4, which is greater than k equals 2. Similarly, the distance between indices 4 and 7 is 7, 4 equals 3, which is also greater than k equals 2. Since all 1's are at least k places apart, the output in this case is true. This demonstrates that the condition is satisfied for this example. Now consider a second example with nums equals 1, 0, 0, 1, 0, 1, and k equals 2. Here, the first one is at index 0, the second one at index 3, and the third one at index 5. The distance between indices 0 and 3 is 3, 0 equals 3, which is greater than k equals 2. However, the distance between indices 3 and 5 is 5, 3 equals 2, which is not greater than k equals 2. Since we've found at least one pair of 1's that do not satisfy the condition, the output for this input is false. This highlights that all pairs of 1's must meet the distance requirement for the result to be true. In another scenario, let's look at nums equals 1, 1, 1, with k equals 1. Here, the first one is at index 0, the second one at index 1, and the third one at index 2. The distance between indices 0 and 1 is just 1, which is not greater than k equals 1. As soon as we find even one pair of 1's that fail to meet the condition, we can conclude that the output is false. This example shows that for smaller values of k, the placement of 1's must be carefully spaced to satisfy the requirement. Finally, let's discuss some edge cases. If the array nums contains no 1's at all, the condition is trivially satisfied, and the output is always true. For example, if nums equals 0, 0, 0, and k equals 3, there are no 1's to violate the condition. Similarly, if the array contains only a single 1, the output is also always true, as there are no other 1's to compare distances with. When k equals 0, the condition is automatically satisfied for any valid pair of 1's, since j, I greater than 0 will always hold. On the other hand, if k is very large, only arrays with 1's separated by a sufficient number of zeros can meet the condition. For instance, in nums equals 1, 0, 0, 0, 1, with k equals 1000, the output is false because the gap between the 1's is too small. These cases help clarify the behavior under different scenarios. To begin, let's consider the brute force approach. The idea here is straightforward. For every pair of indices where the value is 1, we calculate the distance between these indices and check if it meets the condition of being at least k plus 1. This involves two main steps. First, we iterate through the array to identify and store all the indices where the value is 1. Then, for each pair of these indices, we compute the absolute difference between them and verify if it satisfies the required distance. While this method is conceptually simple, it comes with a major drawback. The time complexity is quadratic O(n squared), which means it performs poorly on larger arrays, especially when the size of the array approaches the upper limit of 10 to the power of 5. Additionally, it requires extra space to store the indices, making it less efficient overall. This inefficiency makes the brute force approach impractical for real-world use cases, especially with large datasets. Now, let's refine our approach with an optimized single-pass method. Instead of checking every pair of 1's, we can simplify the process by keeping track of only the most recent one encountered as we iterate through the array. The key insight here is that each one only needs to maintain the required distance from the previous one, eliminating the need for unnecessary pairwise comparisons. To implement this, we initialize a variable last_index to -1, which will track the index of the last one we've seen. As we traverse the array, if we encounter a 1 and last_index is not -1, we calculate the distance from the current index to last_index and ensure it's at least k plus 1. If it isn't, we return false immediately. Otherwise, we update last_index to the current index and continue. If we complete the loop without any violations, the condition is satisfied, and we return true. This approach is highly efficient, with a linear time complexity of O(n), since we only make a single pass through the array, and it uses constant space, as we only maintain a few variables. By combining efficiency and simplicity, the optimized single-pass approach stands out as the best strategy for this problem. Instead of the brute force method's inefficiency, we focus on the key observation that each one only needs to be at least k plus 1 places away from the previous one. This insight transforms the problem into a much simpler task of checking consecutive distances, significantly reducing computational overhead. The realization that we don't need to compare non-adjacent 1s was the turning point, as it allowed us to craft a solution that works efficiently for large arrays. While the brute force approach is easier to visualize and implement initially, it simply doesn't scale well for larger datasets. The optimized approach, while slightly more complex in terms of implementation, achieves the ideal balance of performance and clarity. This makes it the clear choice for solving the problem effectively and meeting the constraints. Here, we are tasked with checking if all the 1s in a binary array are at least k places apart. This means that for any two 1s in the array, the gap between their positions must be greater than or equal to k. To solve this, we can start with a brute force approach. The intuition behind this approach is simple: we identify the positions of all the 1s in the array, and then compare every pair of indices to ensure the distance between them satisfies the condition. Specifically, for each pair of indices, we calculate the absolute difference and check if it's at least k plus 1. If any pair violates this condition, we know the answer is false. The steps involve creating a list to store the indices of all 1s, traversing the array to populate this list, and then iterating through the list of positions to perform the necessary checks. While straightforward, this approach is inefficient for large arrays due to its nested comparisons, leading to a time complexity of O(n squared). After identifying and storing the indices of all 1s, we then calculate the difference between each pair of adjacent indices in the positions list. If any difference is less than or equal to k, it indicates that the 1s are too close, and we return false. Otherwise, if all pairs satisfy the condition, we return true. However, this brute force approach is computationally expensive, especially for larger arrays, as it involves nested loops to compare every possible pair of indices. To address this inefficiency, we can consider an optimized approach. The optimized solution focuses solely on consecutive 1s during a single traversal of the array. The key idea is to track the most recent index of 1 using a variable, which allows us to check the distance between consecutive 1s directly, without additional storage or nested iterations. By doing so, we reduce the complexity significantly while retaining the correctness of the solution. With the optimized approach, we start by initializing a variable, prev_index, to -1 to indicate that no one has been encountered yet. As we traverse the array, whenever we find a 1, we check if prev_index is still -1. If it is, we simply update it to the current index since this is the first one we've seen. Otherwise, we calculate the distance between the current index and prev_index. If this distance is less than or equal to k, it means the condition is violated, and we return false. If not, we update prev_index to the current index and continue. If we finish traversing the array without finding any violations, we return true. This approach is highly efficient as it eliminates the need for nested loops and uses only a single variable for tracking, resulting in a time complexity of O(n). Additionally, the space requirements are minimal, making it a space-efficient solution. Key insights include the early exit mechanism and the ability to handle edge cases, such as arrays with no 1s or only a single 1, where the condition is trivially satisfied. To compare the two approaches further, the brute force solution uses a list to store the indices of 1's, which requires additional space proportional to the number of 1's in the array. On the other hand, the optimized approach uses only a single integer variable, prev_index, making it significantly more space efficient. Both approaches involve traversing the array, but the brute force solution requires nested loops for pairwise comparisons, whereas the optimized solution processes each element in a single pass. The computation of index differences is common to both methods, but the optimized approach restricts this to consecutive 1's only, avoiding unnecessary comparisons. The pseudocode for the optimized solution highlights its simplicity. We initialize prev_index to -1, traverse the array, and for each one, we either update prev_index or calculate the distance to the last one, returning false if the distance is insufficient. If the traversal completes without finding violations, we return true. This streamlined process makes the optimized approach both elegant and highly performant. To better understand the optimized approach, let's walk through an example. Consider the input array nums equals 1, 0, 0, 1, 0, 0, 1 with k equals 2. Initially, we set prev_index to -1. As we traverse the array, we encounter the first one at index 0 and update prev_index to 0. The next two elements are 0's, so we skip them. At index 3, we find another one. The distance between indices 3 and 0 is 3, which satisfies the condition. We then update prev_index to 3. After skipping the next two 0's, we find another one at index 6. The distance between indices 6 and 3 is also 3, which is valid. Since the traversal completes without any violations, we return true, indicating that all 1's are at least k places apart. This example demonstrates how the optimized approach efficiently checks the condition in a single pass, using minimal space and computation. This code is a solution to LeetCode problem number 1437. Check if all 1's are at least length k places away. The function k_lengthapart takes two inputs, nums, a binary list of zeros and ones, and k, the minimum required distance between any two 1's. Step-by-step explanation *. 1. Initialization *. The variable previous is initialized to none. It will store the index of the most recently encountered one in the array. 2. Iterating through the array *. Using a for loop, the code iterates through the list nums with the index I and the value number at each position. 3. Finding a 1 *. When number equals 1. If previous is not none, indicating this is not the first one, the code checks the distance between the current one and the previous one. This is calculated as I previous 1. If this distance is less than k, the function immediately returns false because the condition is violated. If the distance check passes, or if this is the first one, the code updates previous to the current index I. 4. Returning the result *. If the loop completes without finding any distance violations, the function returns true, indicating all 1's are at least k places apart. Efficiency *. The function runs in O(n) time, where n is the length of the nums array, because it processes each element exactly once. The space complexity is O(1), since no additional data structures are used. This implementation handles all edge cases, such as arrays with number 1's, arrays with only one 1, and arrays where the distance condition is satisfied throughout. This Java implementation solves the problem by iterating through the array and checking the distance between consecutive 1's. If any two 1's are closer than k positions, it immediately returns false. The solution is efficient, with a time complexity of O(n), where n is the length of the input array. Key differences from the Python implementation include the use of explicit variable types and the absence of Python's enumerate function, replaced by a standard for loop. To solve this problem, we start with example 1, where nums is 100100001 and k is 2. The first step is initialization, where we set previous to none, meaning we haven't encountered any 1's yet. Now, as we iterate over the array, at index I equals 0, we encounter the first one. Since previous is none, we update previous to 0 to mark the position of this one. At index I equals 1 and I equals 2, we encounter zeros, so no action is needed, and we simply continue. At index I equals 3, we find another one. We check the distance from the previous one using the formula I previous 1, which gives 3 0 1 equals 2. Since this distance is at least k, we update previous to 3. For the next indices, I equals 4, I equals 5, and I equals 6, all values are 0, so no action is needed. Finally, at I equals 7, we find another one. Again, we calculate the distance from the previous one, 7 3 1 equals 3. This distance is also at least k, so we update previous to 7. Now that we've processed the entire array in example 1, we perform a final check and confirm that all 1's are at least k places apart. Therefore, we return true. Moving to example 2, where nums is 1 0 0 0 1 0 1 and k is 3, we again initialize previous to none. At index I equals 0, we encounter the first one. Since previous is none, we update previous to 0. For indices I equals 1, I equals 2, and I equals 3, the values are 0, so no action is required. At index I equals 4, we find the next one. We calculate the distance from the previous one using I previous 1, which gives 4 0 1 equals 3. Since this distance meets the requirement of being at least k, we update previous to 4. At index I equals 5, the value is 0, so we continue. Then, at I equals 6, we find another one. Here, we check the distance from the previous one using the formula I previous 1, which gives 6 4 1 equals 1. This distance is less than k, so the condition is violated. As a result, we immediately return false. Finally, in example 3, nums is 1 1 0 0 0 1 and k is 1. Once again, we start by initializing previous to none. At index I equals 0, we encounter the first one and update previous to 0. At index I equals 1, we find another one. We calculate the distance from the previous one as I previous 1, which gives 1 0 1 equals 0. This distance is less than k, so we return false immediately without further processing. This demonstrates how the solution efficiently terminates as soon as the condition is violated. To analyze the time complexity of this solution, we start with the main operation, which is iterating through the array. The algorithm uses a single for loop to traverse the input array nums, and if we let n represent the length of nums, the loop will execute exactly n iterations. During each iteration, only constant time operations are performed, such as checking if the current element is 1 and calculating the distance between indices. For example, the condition I previous 1k involves simple subtraction and comparison, both of which are O1 operations. Similarly, updating the previous variable is also performed in constant time. Since there are no nested loops and each element is processed in O1 time, the total time complexity for the entire traversal is O(n). Now, let's focus on the space complexity of this solution. The algorithm uses only a single variable, previous, to keep track of the index of the last one encountered in the array. This variable requires constant space, or O1. Additionally, the input array nums is passed by reference, meaning no additional memory is allocated for it. Importantly, the algorithm does not use any extra data structures, such as lists or hash maps, whose size would depend on the input. Therefore, the space usage remains constant regardless of the size of the input array, resulting in an overall space complexity of O1. When we compare this optimized approach to a naive solution, the differences in both time and space complexity become clear. A brute force method might involve using two nested loops to compare every pair of 1's in the array, leading to a time complexity of O(n squared). Additionally, a naive approach might store the indices of all 1's in an extra data structure, potentially requiring O(m) space, where m is the number of 1's in the array. In contrast, the current optimized solution eliminates the need for nested loops and extra space. By directly checking the conditions in a single pass, the time complexity is reduced to O(n), and the space complexity to O1. Looking at best, average, and worst-case scenarios, the efficiency remains consistent. In the best case, if there are number 1's, the loop only iterates through the array without additional checks, maintaining O(n) time. On average, the algorithm handles a mix of 0's and 1's, and the overall time complexity stays O(n). Even in the worst case, where the array consists entirely of 1's, the distance checks for each one are constant time operations, ensuring the time complexity remains O(n). Finally, we can mathematically validate the big O notation for this algorithm. Since the algorithm performs a single pass through the array nums, the total number of operations is directly proportional to the length of the array, denoted as n. Each step involves constant time operations, such as comparisons and updates, so the overall time complexity is O, n. For space complexity, the algorithm only uses a fixed number of auxiliary variables, like previous, which do not grow with the size of the input. As a result, the space complexity is O1. This proves that the algorithm is both time and space efficient, making it well suited for large input sizes. When tackling this problem, there are a few common mistakes that can lead to incorrect solutions or inefficiencies. First, not accounting for edge cases is a frequent issue. For example, if the input array contains no 1s, such as nums equals 0, 0, 0, the problem becomes trivial, but failing to account for this can result in unnecessary computations or even errors. Another mistake is making incorrect index comparisons. For instance, using nums I, nums j, instead of the absolute difference, abs I, j, can produce flawed logic, especially when checking the k condition. Similarly, reversing the logic for the k spacing check will lead to false positives or negatives, particularly in smaller arrays. Finally, overlooking the need for early termination is a critical inefficiency. If a violation of the k rule is found, continuing to iterate through the array wastes valuable computation time, especially with larger inputs. Addressing these issues can greatly improve both accuracy and performance. Another common pitfall is relying on inefficient pairwise comparisons, such as using nested loops to check the spacing between every pair of 1s. While this approach may seem straightforward, it results in a time complexity of O(n squared), which is far too slow for large arrays. Instead, a linear solution is not only possible but also much more efficient. Additionally, misunderstanding the problem's k-spacing rule can lead to mistakes. Some assume that k represents the total distance between the indices of 1s, forgetting that the actual gap should be the distance minus 1. For example, if two 1s are 5 indices apart, the gap is 4, not 5. Misinterpreting this rule results in incorrect spacing checks and invalid results. Keeping these points in mind is crucial for avoiding common errors and building a robust solution. To succeed in interviews, it's important to focus on strategies that highlight both efficiency and clarity. A key insight for this problem is to maintain a single variable to track the index of the last one. This allows you to compute the gaps between 1s and O(n) time without requiring additional space. This approach not only optimizes performance but also demonstrates your ability to simplify the logic. Recognizing patterns is another valuable skill. Many array-based problems can be solved by scanning the array while maintaining a specific state, such as the last one index in this case. Mastering this technique will help you approach similar problems effectively. Additionally, interviewers often value optimization strategies like early termination, which show that you're thinking critically about performance. Don't forget to address edge cases, such as empty arrays, arrays containing only 1s, or situations where k is extremely large. Discussing these scenarios demonstrates thoroughness and attention to detail. This problem is closely related to several other LeetCode challenges that you might find useful to practice. For example, LeetCode 485, max consecutive ones, focuses on identifying sequences of 1s in an array. LeetCode 1004, max consecutive ones 3, introduces a sliding window variation where you can flip up to k zeros, making it a great exercise for learning dynamic window management. Another related problem is LeetCode 1295, find numbers with even number of digits, which involves traversing an array while performing condition-based checks. Lastly, LeetCode 1343, number of subarrays of size k and average greater than or equal to threshold, requires careful handling of window sizes and conditions, offering another perspective on array traversal. Exploring these problems will deepen your understanding of array-based techniques and broaden your problem-solving toolkit. Alongside these, it's worth comparing alternative approaches to this problem. For instance, the brute force method involves comparing every pair of 1s, which is simple to implement but has a time complexity of O(n squared, and becomes impractical for larger inputs. A more efficient solution uses an optimized linear scan. Here, you track the index of the last one as you iterate through the array. This allows you to calculate gaps between 1s and O(n) time while avoiding nested loops. The trade-off is that you'll need to handle indices carefully to ensure accuracy, but the performance boost makes it worthwhile. Another approach to consider, especially for variations of this problem, is the sliding window technique. This method is particularly useful when the problem involves variable window sizes or dynamic conditions, such as maximizing certain values or meeting thresholds. Like the linear scan, the sliding window typically achieves O(n) complexity but may require more effort to implement correctly. By understanding the strengths and trade-offs of each approach, you can choose the most suitable one based on the specific requirements of the problem or variation you're working on. Great job! We've successfully solved the problem check if all 1's are at least length k places away. Today, we explored efficient array traversal techniques and highlighted key takeaways to apply in similar scenarios. Keep practicing, stay curious, and don't hesitate to revisit this solution for deeper understanding. See you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!